4.4a today. So you plan to enclose a rectangular corral with 800 yards of fencing. And use a straight river as one side. You plan to enclose a rectangular corral with 800 yards of fence and use a straight river as one side. And the question is, what is the largest area you can enclose? Okay, so what does this word largest area here signify that we're going to do in a calculus way? It means we're going to find a maximum, right? If they're looking for the largest of something, then we're looking for the max. So before we can figure that out, though, we should draw a picture of what's happening here. So I guess there's a river. And then the river is going to count as a barrier, and you're just going to fence in 3 of the sides. So you're going to put fence here, and here, and here. So I guess you have some animals that can't swim, because they're not going to escape by the river, apparently. I don't know whether there are any animals that can't swim, but these animals can't swim. All right, so you don't know how long this side is, so you're going to call it X. And you don't know how long this side, so you're going to call it X. So far you've used up 2x of the fence. So that means you have 800 minus 2x left for the third side, because all 3 sides have to add up to 800. So for example, if you put 100 yards here and 100 yards here, then you've used up a total of 200 yards. So then you have 600 yards left for this side. 800 minus the 200. Okay, so in general, 800 minus 2x. So then this question is asking for the largest area. So if we're going to find the largest area, we need a formula for area. So the area of this rectangle is just the x times the 800 minus 2x. Because the area of a rectangle is just length times width. So then you distribute the x, so that would be 800x minus 2x squared. And we're looking for the largest possible area. So before calculus, what you would have done is you would have gotten a graph of this area function. And it would have looked like this. Because it's an upside down parabola, right? And then where is the largest area? At the highest point, right? Okay, that's before calculus. You just graph the area function and you look at where the highest point is. But now how in calculus do we find the highest point? Yeah, the highest point here is happening when the slope is 0, right? So we would set the slope equal to 0. Or on some graphs, the highest point happens when the slope is undefined. So we would take the derivative and set it equal to undefined. Okay, so whenever you're trying to find a max or a min, you find the critical values, which is where the derivative is 0 and where the derivative is undefined. All right, so we'll take the derivative of this area, and that's 800 minus 4x. And then you just make a note that the derivative is never undefined, just so the reader knows that you know to consider that. This is never undefined because it's just a straight line. And then the other critical values come from the derivative being 0. So that's at 200. So we suspect that this is probably going to be where the maximum happens because it's the only critical value. But we have to prove that it's a max. We can't just assume that the answer we're getting is a maximum. So in order to prove that it's a max, you put 200 on a number line. And then you try a number below 200 and a number above 200. So plug 100 into the derivative, and that's 800 minus 4 times 100. So that's 400. So the derivative is positive before 200. And then 800 minus 1200 is negative 400. So the derivative is negative after 200. Okay, so when you read the question and it says, what is the largest area you can enclose, is that asking for an absolute max or is that asking for a local max? Absolute max, right? It's saying, what is the largest overall? It doesn't say overall, but it means find the largest overall. So we're actually looking for an absolute max. So this right here is called the first derivative test. And this verifies that 200 is a local max. But if there's only one critical value, and the graph is always going up before that, and then always going down after that, then in this special case, the 200 is also an absolute max, right? Just because it doesn't switch anywhere else. So it's always going up, and then it's always going down. So in this case, the 200 is an absolute max as well, because of that. So there is an absolute max at x equals 200. But we haven't quite answered the question yet, because the question is wanting to know what the largest possible area is, not what x should be to make the possible area, the largest possible area. So now we need to plug the 200 into the area function. So one of the sides is 200, right? This side of the 10 is 200. And then the other side is 800 minus 400. So 400. That comes out to 8 with 4 zeros. So 80,000 square yards is the largest possible area. Okay, so in 4.4, we're still finding maximums and minimums. It's just now there's some words associated with it. So it's a word problem that's max and min problems, which I know you guys really love word problems, so you'll be really excited to know that. So. All right, so let's look at example 2 also. Okay, so this one is a rectangular box is made by cutting squares out of a sheet of cardboard, out of the corners of a sheet of cardboard. The sheet is 24 inches by 15 inches. So for part A, we're going to find the dimensions of the box with largest possible volume. And then B, we're going to find the maximum volume. A rectangular box is made by cutting squares out of the corners of a sheet of cardboard, and the sheet is 24 by 15. We're going to find the dimension of the box with the largest possible volume. So we have the sheet of cardboard. Looks like this. It's 24 inches on one side and 15 inches on the other side. And then what they're going to do is they're going to cut squares out of the corners. So cut a square here, and a square there, and a square there, and a square there. So then that's cut out. Then if you fold this flap up and fold this flap up down here too, and on the side, then you get a box. Is everybody picturing that okay? It's totally fine if you're not picturing it okay. It's early in the morning on a Monday. I can get out a sheet of paper and cut out the corners and fold it if you'd like. I've done it before, I'll do it again. Is everybody okay? All right, so we got a box. So the bottom of the box is this rectangle that is in the dotted lines, right? And the question's asking for the largest possible volume. So if we're going to find the largest possible volume, we need a formula for the volume. So this is the key when you're doing these types of problems. You need to determine what formula is the focus. In the last problem, it said find the largest area. So we were focusing on the area equation. In this problem, it asks for the largest volume, so that means we're going to focus on the volume equation. All right, so that's our key, the volume equation. So how do you figure out the volume of a rectangular box? It's length times width times height, right? So length times width times height. So that means I need to take this side times this side. All right, so what we don't know is how big the square is that we cut out. That's what our decision is. How much square should we cut out in order to make the biggest possible volume box? So since we don't know that, we're going to put an X here. X is going to represent how big the square is, the length of one of the sides of the square. So you cut out X this way and X this way, and then you got a square cut out. Same thing here. All the squares are equal, X and X, X and X, X and X. Okay, so this side over here used to be 15. The original sheet of cardboard was 15 inches. So I cut out an X on this side, and I cut out an X on this side. So I cut out two X's. So now this length is 15 minus 2x. For example, if I cut out 5 inches on both sides, then that length would be down to 5. Or if I cut out 3 inches from both sides, then it would be subtracting out 6. So this would be 9. Okay, so the width of the box is 15 minus 2x. Everybody okay with that? Okay, then this is 24, right? So I cut out x's on each side. So this is 24 minus 2x. So now looking at the bottom of my box, after I fold up the flaps, I've got 15 minus 2x times 24 minus 2x. For my length and my width, right? But I still have to multiply by the height. So after I fold this flap up, how tall is the box? X, right? Because that X there is going up. So my height is X. So there's my volume formula. 15 minus 2x times 24 minus 2x times x. And I'm trying to find the maximum of this. Okay, so next thing I want to talk about is the domain of this problem. The domain is what x is allowed to be. So x has a limit because I can only cut out a certain amount. If I cut out 7 on both sides, then I'd be down to 1 inch. That'd be okay. It would be kind of a weird looking box. It would be really skinny. That's okay. Or if I cut out 7.4, then I'd have a really, really skinny box. If I cut out 7.5, then I've used up everything, right? Then I don't really have a box. I have a flat piece of paper that's folded up, or piece of cardboard. But 7.5 is the farthest I could possibly go, right? Of course, we're not going to do that because that'll give us a volume of 0. But I'm going to say that the biggest possible x is 7.5. I'm going to pretend that 7.5 is okay. then we're going to fold up the sheet of cardboard. And it's not really a box. The volume is 0. But we'll say it's okay. Because I don't want to say 7.4, because 7.45 would be okay. And I don't want to say 7.45, because 7.46 would be okay. And we'll go back and forth like this forever. So let's just settle on 7.5. Okay, and then the smallest x could possibly be a 0. I mean, again, then I would have a weird box. I would have a flat sheet of cardboard. If I didn't cut anything out, I wouldn't have anything to fold up. But I could cut out anything bigger than that. Okay, so here's my domain, 0 to 7.5. Now, the reason I wanted to do this, well, this question's asking for the largest possible volume, right? So that's an absolute max. And on this problem, we're looking for an absolute max on a closed interval. So because of that, we can use the closed interval method. So on number 1, yeah, go ahead.
So is the domain of the length?
Yes. Well, it's what the length is allowed. Sorry, it's actually the height. Because it's what you're allowed to cut out. And then the amount that you cut out ends up folding up and being the height.
So it couldn't fold this?
Well, you could cut out 12 this way, yes. But you couldn't cut out 12 this way. Because there's not enough to go 12 from each end, because there's only 15.
So why are you setting up 15 minus 12 equals 0 and not the 24 minus 12 equals 0?
So if you cut out 12 inches this way, then you'd only have 3 inches left on this other side. So you can't cut 12 inches out this way. So 12 doesn't work. I agree with you that you could cut out 12 this way and 12 this way. But you're supposed to cut out the same amount this way as you cut out this way. So yes, you could cut out 12 this way, but you couldn't cut out 12 this way. So that's why I'm focusing more on this limit. Good. I think I totally answered your question now. All right, good. All right, so yes, this is the domain of the x of what you're cutting out. You said the length originally, and I sort of, yeah, sort of, but it's actually the domain of the x. And not to get over technical with you, but that's what a domain is. It's what x is allowed to be. Good. Okay, so we've got a volume formula, and we're trying to figure out an absolute max on a closed interval. So in example 1, we didn't have a closed interval, so we couldn't use the closed interval method to find our absolute max. But on this one, we have a closed interval, so we can use the closed interval method to find our absolute max. Okay, so the closed interval method, the way that goes is you have to find the critical values and then the endpoints. So we've already got the endpoints, that's good. So we're going to have to find our critical values from this formula, so we'll have to take the derivative of this. Before I take the derivative of it, I'm going to FOIL it out. So 15 times 24, I have it here in my paper, is 360. And then this would be minus 30x, minus 48x, and plus 4x squared. And then you times that by x. And then you can distribute the x. So that would be 360x minus 30x squared minus 48x squared plus 4x cubed. Then you can collect like terms, so 368 minus 78x squared plus 4x cubed. So this is just the original volume formula, right? Rewritten in a different way. So if I'm going to find the absolute max, I need to take the derivative of this volume to find the critical values. So derivative of the volume is 360 minus, let's see, 2 times 78 would be 156, I think. There's my derivative. Just check on that since it's early in the morning here. So then I got to set that volume prime equal to 0 and undefined to find the critical values. So volume prime undefined never happens. But my advice is to you, even if it doesn't happen, write it down, because then someday it'll happen and you'll forget about it. So then I have to set the volume prime equal to 0. I'm going to factor a 12 out of that. Uh, 360 divided by 12 is 30. And 156 divided by 12, let's see, that's 13. I think that's right. So I just pulled a 12 out of everything. So now I'm going to factor this. I need two numbers that multiply to be 30 and add up to be 13. So that's 10 and 3. Negative 10 times negative 3 is positive 30. And negative 10 plus negative 3 is negative 13. So then you find out that the critical values are when x equals 10 and when x equals 3. So how do you feel about 10? It won't work, right? Our domain is 0 to 7.5. So we don't need to worry about that critical value. So we've only got the critical value 3. Okay, so how does the closed interval method work? The first step is find critical values. We did that. Second step is find the endpoints. So then what's the third step? Plug those three numbers, or however many you got, into the original volume function. So we're going to take x and v of x and plug 0 and 3 and 7.5 into that. My advice is to use this volume formula. If you don't have a calculator, it's easiest to plug into this. So volume at 0 is 15 minus 2 times 0 times 24 minus 2 times 0 times 0. So I don't really even care what these numbers are, right? Well, they're easy enough. It's 15 and 24. But the fact that I'm going to be multiplying by 0 at the end tells me that if I have a 0, it's going to be 0. Which makes sense, right? Because the 0x meant I wasn't going to cut out anything. So I just have my flat piece of cardboard, which has volume 0. Okay, then if I plug 3 into the volume, that'll be 15 minus 6 times 24 minus 6 times 3. So 9 times 18 times 3. So I know 3 times 18 is 54. 54 times 9 is 486. And then for the 7.5, I don't really necessarily care about these other two numbers, right? Because I know 2 times 7.5 is 15, and 15 minus 15 is 0. So I have 0 times something times 7.5, so that's going to come out to 0. So the maximum volume is 486, because it's the largest out of those three. So that's part B, right? That's the question B said find the maximum possible volume. So that's 486 cubic inches. And then part A says find the dimensions. The dimensions are the length and the width and the height. So that's 9 by 18 by 3. Because when I cut out 3 inches here, I started out with 15, right? If I cut out 3 inches here, I'll be down to 12. If I cut out 3 inches here, I'll be down to 9. So this is 9. And then with the 24, if I cut out 3, it's down to 21, then down to 18. So this is 18. And then if I cut out 3, my height is 3. Okay, so anyway, the dimensions are 9 inches by 18 inches by 3 inches. Okay. Okay, for the last one here, we've got an open rectangular box is to be constructed. So this word open means that there's not a lid on it. There's not a top. Just like the last one, there wasn't a lid. The box has square ends. And holds 6,400 cubic centimeters. Oops, I left out the word holds. So this 6,400 cubic centimeters, what is this? What concept is this? It's the volume of the box, right? How much goes inside, how much it holds. All right, the cost is 75 cents per square centimeter for the base, the bottom of the box, and 25 cents per square centimeter for the sides. So what we're going to find is find the minimum cost construction. Okay, so in example 1, we wanted, what were we focused on in example 1? Area, right? Because it said find the maximum area. In example 2, we were focused on volume, because it said find the maximum volume. So what are we focused on in this one? Cost, right? So our main concept here is cost. We need an equation for cost so that we can find the minimum of the cost. All right, so let's draw a picture here. We've got a rectangular box and it has square ends. That means that the front of it is a square and the back of it is a square. So front's a square, back's a square, and then the top and the bottom and the left and the right are rectangles. Okay, so apparently the bottom of this box is more expensive to make. Maybe that's because it's going to have a more solid bottom. Because the bottom costs 75 cents per square centimeter. Okay, so let's call this length X for the square and this length Y. So then on the bottom, the number of square centimeters is X times Y. That's the area of the bottom. For example, let's say this was 5 and this was 10. Then the bottom would be 50 square centimeters. And it costs 75 cents per square centimeter to make it, right? So you take that 50 square centimeters and multiply it by 75 cents to figure out the cost. So you take this area and multiply it by 75 cents, and then you've got cost. So this is the cost for the bottom. And then for the front, the area is X squared. And then that costs 25 cents per square centimeter. So you're going to multiply that by 25 cents to get the cost. And the back is the same way, right? X times X is X squared times 25 cents. I've got the cost of the bottom, the cost of the front, the cost of the back. Now I've just got the cost of the left and the right, left. So this is Y times X for area, and that costs 25 cents for that, for the left and the right. So I'm going to add all those together. So total cost is, let's see, 0.75 plus 0.25 plus 1.25 xy plus 0.5 x squared. So there's my cost. Now this is the first time we've had two variables. So before we can figure out the max or the min of this, we need to get rid of this variable, the y. And that comes from the fact that we know that the volume is 6,400. So the volume of this box is x times y, which is 6,400. So x squared times y equals 6,400, and then divide. So then you can take that and plug it in over here for y. So my cost equation is 1.25x times 6,400 over x squared plus 0.5 times x squared. So then my final cost equation, oops. I think I have 1.25 times 6,400 over here. 8,000. So there's my cost equation. So what am I trying to find in this problem? The minimum cost, right? So then I'd have to take the derivative of this, set it equal to 0 and undefined, et cetera, to find the minimum. Is everybody okay with knowing how to do that? I don't have time to do it all, but